I use Google's new Colab MCP server to let an AI agent build, run, debug, and submit a quantum chemistry notebook to real IBM Quantum hardware. Google recently announced the Colab MCP server. It is an open-source bridge that lets any MCP-compatible AI agent control a live Google Colab notebook. That sounds useful on paper, but I wanted to see whether it could handle something more demanding than a typical dataset demo. So I gave an agent a real task. Build a quantum chemistry notebook from scratch, install the right dependencies, debug compatibility issues, run a full parameter sweep, and submit a job to real IBM Quantum hardware. It worked. A blank Colab notebook became a fully working quantum chemistry workflow, complete with dependency fixes, a 15-point scan, and a real IBM Quantum job submission. From a blank notebook to a real hardware result, the agent created and structured the notebook, installed the required packages, fixed multiple version and runtime errors, ran a 15-point hydrogen molecule scan, and submitted a real job to IBM's 156-qubit quantum processor. That is what made this experiment interesting to me. Not just the quantum part, but the workflow itself. Colab MCP turned Colab from a notebook I manually edit into a cloud lab an agent could actively operate. See the notebook. Here is the actual Colab notebook the agent built and ran during this experiment. Why this was a good test for Colab MCP. Most product demos stay in safe territory. Load a CSV, draw a chart, maybe install one package. I wanted something messier. Quantum chemistry is a good stress test because it combines several failure points at once. Dependency management, scientific Python tooling, cloud execution, notebook organization, runtime debugging, and optional handoff to real hardware. If Colab MCP could survive that stack, it would tell me much more about its real-world usefulness than a toy notebook ever could. The setup. Colab MCP. Google's new Colab MCP server gives an MCP-compatible agent programmatic control over a Google Colab notebook, not read-only access. Real notebook control. That means an agent can create and edit cells, write markdown and code, execute cells, inspect outputs and tracebacks, and iterate until the notebook actually works. The setup is simple. Add the MCP server to your agent config. Prerequisites are minimal: Python, Git, and UV. Once the server is configured, it connects to the Colab notebook you already have open in your browser. The task: compute the H2 potential energy surface. I chose the hydrogen molecule H2. This is the smallest meaningful benchmark in quantum chemistry. It is simple enough to run quickly, but still rich enough to show whether the quantum workflow is doing something real. The goal was to compute how the molecule's energy changes as the bond between the two hydrogen atoms is stretched. This is called the potential energy surface. Why does that matter? Because it lets you compare three things directly: a standard classical approximation, a quantum algorithm, and the exact reference solution. That makes H2 the perfect test case for both the scientific result and the tooling around it. What the agent actually did. I opened a fresh Colab notebook, connected the MCP agent, and gave it the task. From there, the agent generated, executed, and debugged the notebook inside Colab, while I only provided the task and access setup. First, it resolved the dependency mess. The first real issue was package compatibility. The Qiskit ecosystem is currently split. Some chemistry-related libraries still depend on the 1.x line and do not yet cleanly support Qiskit 2.x. And the agent figured that out quickly and pinned a working combination. The versions that worked were Qiskit 1.4.5, Qiskit Nature 0.7.2, Qiskit Algorithms 0.4.0, and PySCF 2.1.2.1. This is exactly the kind of friction that normally burns time when working manually. The agent saw the environment, adjusted, and moved on. Second, it built the molecular Hamiltonian. Next, the agent used PySCF to compute the electronic integrals for H2 at equilibrium bond length and map the molecule into a qubit Hamiltonian. The result was a 4-qubit problem with 15 Pauli terms. Small enough to simulate exactly, but still a real quantum chemistry workload. Third, it ran VQE, and debug the first major failure. At equilibrium geometry, the agent ran three methods: Hartree-Fock, VQE on a simulator, and exact diagonalization. The VQE result matched the exact answer on the simulator, while Hartree-Fock left a noticeable gap. That is the core promise of quantum chemistry workflows like this. Quantum methods can recover effects that standard approximations miss. But the first VQE attempt did not work. The agent hit an algorithm error because the primitive job used to evaluate the energy failed. The cause was a version mismatch between the primitive being used and the API style expected by Qiskit algorithms. The fix was to switch to state vector estimator, rerun the notebook, and continue. That debugging loop is the real value of Colab MCP. The agent does not just generate code. It sees the traceback, changes the notebook, and re-executes until the workflow is alive again. Fourth, it scanned the full potential energy surface. Once the equilibrium point worked, the agent swept 15 bond distances from 0.3 angstroms to 3.0 angstroms. This is where the scientific point became obvious. As the bond stretches, Hartree-Fock gets much worse. At 3.0 angstroms, it is off by 277 millihartree. VQE stays essentially aligned with the exact result across the full curve. So this was not just an orchestration demo. The experiment also captured a real chemistry phenomenon that motivates quantum algorithms in the first place. Then I pushed it to real quantum hardware. After the simulator run, I wanted to see whether the same workflow would survive contact with real hardware. The agent connected to IBM Quantum using a token stored in Colab secrets. Available backends included systems such as IBM Fez, IBM Torino, IBM Kingston, and IBM Marrakesh. The agent selected IBM Fez. Then things got messy again. More breakage, more fixes. The IBM Runtime transpiler plugins were not compatible with the Qiskit 1.4.x environment used by the chemistry stack. That caused a transpiler error involving an invalid plugin name for IBM Dynamic Circuits. The fix was to bypass the plugin path and transpile directly against the backend's basis gates and coupling map. Then another issue appeared. IBM's open plan did not support sessions in this setup, so the agent switched from a session-based flow to estimator version 2 using the backend directly. Again, this is where the workflow becomes meaningful. The agent was not just writing a notebook. It was navigating a real compatibility chain across Colab, Qiskit, and IBM Runtime. The hardware result. The final hardware run returned a real completed job on IBM Fez, a 156-qubit backend. At equilibrium geometry, the exact classical result and the simulator VQE result matched at about -1.137306 Hartree. The hardware result came back at about -1.123506 Hartree. That meant a hardware error of about 13.8 millihartree, or 1.21% relative error. So the hardware result landed in the right range, but it was clearly degraded compared to the ideal simulator. That is not a failure. That is the current reality of NISQ-era quantum computing. The algorithm worked, the notebook worked, the cloud workflow worked, but physical qubits still introduced noise through gate error, decoherence, and measurement error. And that contrast was valuable to see in one end-to-end run. Why this experiment was meaningful. There were two reasons this was worth doing. First, it showed a real scientific difference. H2 is small but meaningful. It is the smallest benchmark that still exposes whether the algorithmic stack is doing real work. The simulator showed that VQE could recover the exact solution for this system, and the full bond scan highlighted where classical approximation methods begin to fail. Second, it showed a new way to work with agents. This was the bigger surprise. Colab MCP made it practical to hand a messy technical objective to an agent and let it operate inside a cloud notebook until the notebook actually worked. That included package installation, notebook structure, traceback-driven debugging, reruns after fixes, cloud execution, and optional handoff to real quantum hardware. That is much more interesting than simple code generation. It points toward a new working style where Colab becomes an executable cloud workspace for AI agents, not just a place humans paste code into. What I learned: Colab MCP is genuinely useful. This did not feel like a gimmick. The agent created 17 cells, handled several compatibility issues, ran a 15-point scientific sweep, submitted a real quantum job, and produced usable outputs quickly. That is exactly the kind of workflow where local-only agent setups start to feel cramped. The package ecosystem is still the roughest part. The biggest friction was not the quantum algorithm. It was Python package compatibility across Qiskit, chemistry libraries, and IBM runtime tooling. That is where a notebook controlling agent helps most. It can read the errors and iterate much faster than a human, manually bouncing between terminal, browser, and documentation. Real hardware is still noisy. The simulator matched the exact answer. The hardware result came back with 1.21% relative error on a very small problem. That is a useful reminder that the software stack may be getting smoother, while the hardware frontier is still about error mitigation and long-term fault tolerance. Colab is an underrated chemistry environment. PYSCF installs cleanly in Colab's Linux runtime and avoids the setup pain many people hit on Windows. For this kind of workflow, the combination of Colab plus MCP is not just convenient. It may actually be the easiest path from idea to result. How to reproduce it. First, set up the Colab MCP server in your agent config. Second, open a Google Colab notebook in your browser. Third, add your IBM Quantum token to Colab secrets as IBM_token. Fourth, give the agent a concrete task and let it build the notebook. In my case, the task was ambitious enough to break a few times, which is exactly why it was useful. Final take. Google's Colab MCP announcement is not just about making notebook automation easier. It changes what Colab can be. Instead of treating Colab as a notebook you manually edit, you can start treating it as a cloud workspace an agent can actively operate. This experiment pushed that idea through a workflow that included scientific Python, version conflicts, notebook authoring, parameter sweeps, and real hardware submission. The result was not magic. It was a real notebook, built in the cloud, debugged in place, and executed end-to-end by an agent. That is why I think Colab MCP is worth paying attention to. If this was my first stress test of Colab MCP, it was a very convincing one.